Welcome to the deep dive. Today we're really getting into the weeds on distributed data systems specifically, how requests find the right data, and how complex queries get handled fast using parallelism.
Yeah, this stuff is bread and butter for senior engineers and definitely pops up in system design interviews.
Absolutely. So our mission today is basically to demystify these concepts for you, especially if you're prepping for those big tech interviews.
Think of this as a safe space to work through these ideas, almost like a practice interview session.
Exactly. And guiding us, we have, well, let's call him our expert, a principal engineer with tons of experience at places like LinkedIn, Netflix, you know the type.
Just trying to share what I've seen work and what interviewers often look for.
And I'll be playing the role of maybe a senior engineer, someone sharp, but still navigating the interview gauntlet. So you, the listener, get to be a fly on the wall.
Right. So let's start with a foundational question. Imagine this distributed database, data spread everywhere. A client wants something. How does it even know which computer, which node to talk to?
That's a great starting point. Because, yeah, it's not just one big server anymore. There are a few different ways systems handle this routing problem.
Okay, let's unpack this. It's kind of like sorting mail, right? The post office needs to know which truck goes to which neighborhood. Your system needs that too. So what's the first way? Maybe random routing with redirection.
Okay, yeah. So with this one, the client basically just picks a node, maybe any node it knows about, and sends the request there. Like picks one at random almost.
And then what happens? That node might not have the data.
Exactly. So the node that gets the request has to check, do I have this piece of data? And to do that, it needs some idea of how the data is partitioned across the whole cluster.
Ah, okay. So it needs the map.
Right. And if it doesn't have the data, it looks at its map, figures out which node does, and then it redirects or forwards the request to that correct node.
And the response, does it go straight back to the client?
Usually, it seems like it goes back to the initial node that did the redirecting, so there's an extra hop there.
Right, like dropping your mail in any mailbox, and the first post office has to figure out where it really needs to go before sending it on. It works, but maybe not the most efficient.
Yeah, the key is that every node needs that partitioning knowledge for the redirect to work.
Okay, so approach number 2. What about using a routing tier?
Yes, the dedicated routing tier.
Mm-hmm.
So here you have this separate layer of servers. Their only job is routing. Clients don't talk to data nodes directly.
They talk to this layer instead.
Exactly. All requests go to the routing tier first.
Okay, so this sounds like maybe a restaurant host, knows all the tables, directs you straight there, no wandering around.
Perfect analogy. This tier is the one that holds the complete map, the partitioning scheme. It looks at the request, knows exactly which data node has the data, and forwards it straight there.
So it centralizes the routing smarts. The data nodes themselves can be simpler then.
Yeah, they don't need to worry about where other data lives. The routing tier handles all that traffic cop duty.
And the response probably goes back through that tier too.
Typically, yes. Keeps things consistent.
All right, that makes sense. What's the third main strategy?
Client-side routing. This one's different because the client is the smart one. The client knows the map. Yeah. The client application itself understands the partitioning scheme. So when it needs data, it figures out the right node and connects directly to it. No middleman.
Ah, like using GPS directly to navigate to your destination, cuts out the intermediary stops. What's the upside?
Essentially lower latency, right? Fewer network hops. You go straight to the source.
Okay, sounds good. But there's always a trade-off. What's the catch here?
The complexity moves. Now it's the client's responsibility to know the layout and, crucially, to keep that knowledge up to date.
Right, keeping it up to date. That seems like the core challenge, doesn't it, for all these approaches? Whether it's the nodes needing the map or the routing tier or the client, how do they find out when things change? Like when data moves or nodes join or leave?
Exactly. That's the million-dollar question. How does the routing information stay accurate when the cluster itself is dynamic? Partitions get rebalanced, nodes fail, things change.
That whole problem falls under the umbrella of service discovery. It's bigger than just databases, really. How do services find each other?
And a really common tool for this is something like ZooKeeper, isn't it?
Yes, ZooKeeper often plays that role. It's a coordination service. Think of it as a highly reliable central registry for the cluster's metadata.
So nodes register themselves there.
Nodes register, yes. But critically, ZooKeeper maintains the authoritative map, the partition assignment table, let's call it. It knows which partition lives on which node.
What kind of details are in that table?
You'd have things like the key ranges for each partition, maybe a partition ID like 0, 1, 2, up to 11, let's say, and then the node currently responsible for that partition and its actual network address, like its IP.
Okay, like node 0 might be at 10.20.30.100.
Exactly. And maybe it handles partitions 0, 3, 6, and 9 in a round-robin fashion. Then node 1 at 10.20.30.101 gets partitions 1, 4, 7, 10.
And node 2 at 10.20.30.102 gets 2, 5, 8, and 11. Makes sense, distributes the load.
Right. So how does this ZooKeeper setup help the routing tier, for example?
Well, the routing tier, or even a smart client, can essentially subscribe to ZooKeeper. It asks ZooKeeper to tell it about any changes to that partition map.
Ah, like a notification system.
Exactly. So if a partition moves, maybe for load balancing, or a new node comes online and takes some partitions, ZooKeeper updates its map and then pushes that update out to everyone subscribed, like the routing tier.
So the routing tier always has fresh information to make the right routing decisions.
Precisely. ZooKeeper becomes that single source of truth for the cluster layout, keeps everyone on the same page.
Like we joked, ZooKeeper because even distributed systems need someone to keep the animals in line. And lots of big systems use it, right? LinkedIn's Espresso, HBase, SoulCloud, Kafka.
Yeah, and even MongoDB has a similar idea, though they use their own config servers and the Mongo's routers, but it serves a similar function.
But ZooKeeper isn't the only game in town, is it? What are the alternatives?
Right. Not everyone wants that central coordinator. Systems like Cassandra and Riak, they use something different, a gossip protocol.
Gossip protocol. Sounds intriguing. How does that work? Is it like actual gossip?
Kind of, yeah. Think of it like news spreading through a neighborhood. Instead of a central bulletin board like ZooKeeper, each node just periodically talks to a few other random nodes.
And they just chat.
They exchange information about what they know about the cluster state. Like, hey, I think node X has partition 5, or node Y just came online. This info gradually propagates node by node across the whole cluster.
So eventually everyone gets the updates just through peer-to-peer sharing.
Right. It's decentralized. When a request hits any node, that node might not know the exact location immediately, but through the gossip it's heard, it can usually figure out where to forward the request.
What's the trade-off there? No central dependency sounds good.
It avoids that single point of failure or bottleneck with the coordinator. But the complexity moves into the database nodes themselves. They have to manage all this gossip traffic and state merging. And consistency.
It's eventual consistency, right? It might take a moment for news to spread everywhere.
Exactly. You might have brief periods where different nodes have slightly different views of the cluster, plus more work for each node.
So gossip protocols, proving that even databases love to share the latest news. Okay, what about other systems? Couchbase.
Yeah, Couchbase is interesting. It often uses a routing layer called Moxie. And apparently, Couchbase doesn't rebalance partitions quite as aggressively or automatically, which simplifies things a bit.
Yeah.
Moxie learns the topology changes directly from the cluster nodes.
And how does a client even find the first node to talk to? Or find the routing tier address?
Often, just plain old DNS is good enough for that initial connection point. Those addresses, the entry points, tend not to change as often as the internal partition assignments.
Makes sense. Okay, this is great background. Let's switch gears now more into direct interview prep mode. Imagine I'm the interviewer. Ready for some questions?
Okay, let's do it. I'll try to channel my inner senior engineer candidate.
All right. Question 1. Walk me through the different ways a client request can be routed to the correct data node in a distributed database. Give me the concise version. Focus on trade-offs.
Okay. 3 main ways. First, random routing plus redirection. Client hits any node, that node forwards if needed. Simple start, but adds latency and nodes need the map. Second, a dedicated routing tier. Clients talk only to this tier. It knows the map and directs traffic, centralizes logic, simplifies data nodes but adds a layer. Third, client-side routing. The client knows the map and connects directly, minimizes hops potentially faster, but makes the client complex and hard to keep updated.
Good summary. Clear, concise, hit the trade-offs. My tip here, really emphasize who needs to know what in each approach, the nodes, the tier, or the client. That clarity is key. Okay, question 2. Compare and contrast using ZooKeeper versus a gossip protocol for managing partition assignments.
Right. ZooKeeper is centralized coordination. It gives you strong consistency, a single source of truth for partition maps, and pushes updates. The downside is it's an external dependency, potentially a bottleneck or a single point of failure for coordination. Gossip, on the other hand, is decentralized. Nodes share state peer-to-peer. This avoids the central dependency, potentially more resilient, but you get eventual consistency, and the nodes themselves become more complex, handling the gossip and state merging.
Excellent comparison. You're highlighting that core tension, centralization versus decentralization, and the impacts on consistency, dependency, and complexity. Perfect. Question 3. Imagine a new node is added to the cluster. Using a routing tier with ZooKeeper, how does the system ensure requests eventually get routed correctly to this new node for its assigned partitions?
Okay, so the new node starts up and registers itself with ZooKeeper. Then, some cluster management process assigns partitions to it, maybe taking some load off existing nodes. This partition assignment update is written to ZooKeeper. Since the routing tier is subscribed to ZooKeeper for these updates, ZooKeeper notifies the routing tier about the change. Hey, partitions XYZ are now on this new node at this IP. The routing tier updates its internal routing table, and from then on, directs client requests for partitions X, Y, or Z to that new node.
Spot on. You trace the flow perfectly. Registration, map update in ZooKeeper, notification, routing tier update, correct routing, shows you understand the dynamic update process. Okay, question 4. What are some challenges with client-side routing, especially in a large dynamic system where partitions might move around a lot?
The big ones are complexity and staleness. Managing that partition map logic inside potentially hundreds or thousands of different clients is tough. Deploying updates to all of them whenever the cluster changes is a significant operational burden. And if updates don't propagate instantly, some clients might have stale routing info, sending requests to the wrong node, leading to errors or needing redirection anyway, which defeats the purpose. It just puts a lot of responsibility, maybe too much on the client side.
Very good points. Thinking about the operational side, the day 2 problems is crucial. Final routing question number 5. You're designing a new distributed key value store. Which routing approach would you lean towards and why?
That's a classic it depends question, right? But I have to choose. Assuming typical requirements for a key value store often lean towards high availability and relatively simple client access, I might lean towards a routing tier with ZooKeeper. It simplifies the client significantly. The routing tier handles the complexity, and ZooKeeper provides strong consistency for the routing information, which helps avoid client confusion. While there's a dependency, mature ZooKeeper deployments are pretty reliable. If extreme resilience to coordinator failure was the absolute top priority, maybe gossip. But the complexity trade-off often favors the routing tier model for manageability, I think.
Great answer. There's no single right choice, like you said. The key is justifying your choice based on requirements and acknowledging the trade-offs you're making. You did that well. Okay, let's shift focus slightly for the last part. We've talked a lot about routing single requests, reads, or writes.
But systems handle more than that, right? Like complex analytics queries.
Yeah. Exactly. Think about massively parallel processing or MPP databases. They're built for heavy-duty analytical queries, joins, filters, aggregations, group by stuff that touches huge amounts of data, not just simple key lookup.
How do they manage that across potentially hundreds of nodes without taking forever?
It's all about parallelism. Yeah. The MPP query optimizer is incredibly sophisticated. It takes a big, complex query and breaks it down into smaller pieces, smaller stages, that can run independently on different chunks of data across many nodes at the same time.
So it parallelizes the work plane itself.
Precisely. If a query needs to scan terabytes of data, instead of one machine grinding through it, you have maybe hundreds of nodes, each scanning their local slice of the data simultaneously, then combining the results. It's like having a huge team working on different parts of a massive puzzle all at once.
That makes sense. Divide and conquer, but massively parallel.
Exactly. And making that parallel query execution fast and efficient is a huge deal, commercially and technically. It's a specialized field.
Okay, so wrapping things up, we've covered a lot. The 3 ways to route requests, random with redirect, routing tier, client side, and the pros and cons.
Right, and how systems keep that routing info current using coordination like ZooKeeper or decentralized methods like Gossip. We saw examples like Cassandra, Riak, Couchbase.
And we finished with a look at MPP systems and how they tackle complex queries using parallel execution across the cluster. Essential stuff for system design interviews.
Definitely. Understanding these concepts and being able to discuss the trade-offs clearly, that's what interviewers are listening for.
Absolutely. So now over to you, our listeners. What are your interview war stories related to partitioning or routing in distributed systems? Share them in the comments. And hey, if this deep dive helped your prep, please leave us a rating or review. It really helps others find the show.
And one final thought to leave you with. As these systems get bigger and more complex, how do you see that balance shifting between centralized control, like with ZooKeeper, and more decentralized autonomy, like Gossip for managing data and requests in the future? Something to ponder.